Hey, this is Mr. Boyce. Welcome to Unit 9 Gas Laws. This is our third video in our final exam review series, and we are going to jump right into it. We got 20 questions, so let's get started. So first off, P, V, and T, let's write the relationships for these gas laws. So remember the combined gas law right here. This is P1 V1 over T1 equals P2 V2 over T2. Now, this is what we use to describe the change in a gas. So when you see a question that says, if you increase the pressure or if you decrease temperature or whatever, what's going to happen to the gas? So this is state one to state two. Now, these are derived from a couple different laws. First off, Boyle's law. This is the top, pressure and volume, and that's P1 V1 equals P2 V2. Okay? And then Charles's law. This is also part of the combined gas law, and this is volume and temperature. V1 T1 equals V2 over T2. So as you go through the problems, a lot of problems, you don't need all three, pressure, volume, and temperature. And so this one's almost a multiple choice. You can just kind of pick what you need. Ideal gas law, this is PV equals nRT, and this is for describing the gas as it is. So if you have a question that says something to the extent of, at this temperature, at this pressure, how many moles will there be, that kind of thing, this is the formula for you. Okay, what is STP and what are their values? STP is standard temperature and pressure. So you will see this a lot of times when you're looking through a question, you're saying, okay, do I have pressure? Do I have volume? What do I have? What am I working with? Uh, it may just say STP and not actually tell you a temperature and pressure, but that's okay because you know what they are. It's in your formula sheet in case you forget, but standard temperature and pressure is 0 degrees Celsius, which is equal to 273 Kelvin, which is what you're usually going to use. And standard temperature or pressure, sorry, is 1 atm. Now remember, we have our conversion factors. So let's take a look here. And there we go. 1 atm is also equal to 760 mmHg and 101.3 kPa. So all three of those would be considered standard temperature, or I'm sorry, standard pressure. And remember, PV equals nRT. This is the R that I'm talking about. And we have three different ones. Depends on whether or not you're using ATM, kPa, or mmHg. And we'll get back to that. Okay. Okay, question number one. Let's get going. 15.35 liters of a gas is at a pressure of 190 kPa. At what pressure did the gas have a volume of 13.78 liters? So I have a volume, I have another volume, got a pressure, and it's asking for a pressure. And if I read the question, I see that this is volume one, this is pressure one, this is pressure two, and this is volume two. So pressure and volume, what I'm going to do is just think PV over T, and which parts do I actually need? I just need pressure and volume. So I'm going to do P1 V1 equals P2 V2. Now what I like to do, V1 equals P2 V2, is decide what is it I'm solving for? What do I want to know? And I want to know P2, right? And so what I'm going to do is divide both sides by V2, and I won't go through and do this for every question. I'm just kind of explaining why I'm doing this. V2, V2 cancels on one side, and I'm left with P2 equals P1 V1 divided by V2. So let's just sort of plug and chug. Everything I have in here is in pretty good shape. It's already in liters. So P1, that's 198 kPa. V1 is 15.35 liters. And V2, let's see, 13.78. Also already in liters, which is great. So therefore, I am going to put that into my calculator, and I'm going to end up with 220.56. It's not a very good way to write that. Okay, now the reason I am giving you the full answer on that one, oh wait, never mind, different question. Okay, so there we go. I just kind of gave you the entire answer for that one. So this is in kPa, and there we go. So let's move on. Okay, a gas has a volume, okay. At 17C, I've got a temperature, although I'm going to need to convert it. What is the volume of the gas? Another volume at standard temperature. Okay, well, there's a temperature. And let's see here. So I'm going to go with this is V1 and T1. And then what is the volume if I change to standard temperature? So T2. So this is going to be volume and temperature. So I really just need to use volume over temperature. I can just pick and choose what I want from the combined gas law. Okay, so that is going to be V1 over T1 equals V2 over T2. So V1 over T1 equals V2 over T2. Now, what I want is V2. And so I'm going to cross multiply to do this, right? And so that means that V2 equals V1 times T2 divided by T1. Okay. So let's go ahead and put these into here. And so that's going to be 13.4 times T2, which is over here. And T2 is standard temperature, which is 0 degrees Celsius, but we don't use Celsius, we use Kelvin. So 273 divided by T1, and my T1 is 17 degrees Celsius, and 17, that doesn't work out for me. I'm going to have to add 273 to that one, and that's going to get me to 290. Okay. Now, very, very important that you are paying attention to the order that you put these in. Let me show you what happened with this one. So the answer for this one, again, I'm just going to go ahead and give you the answer on this one, and that comes out to 12.6 okay, liters. Now, when I was first writing out this answer key, I looked at, okay, volume, and temperature. This is a direct relationship. So if one goes up, the other goes down. If one goes down, the other goes down. They do the same thing. And I'm looking at this and I'm saying, okay, I know the temperature. I know temperature 1 and I know temperature 2. All right. So I know temperature 1, I know temperature 2. This is temperature 1, this is temperature 2. And so what happened is the temperature went down a little bit. And so therefore, I'm expecting my answer to also go down a little bit, which it did, 13.4. But when I was making this review, I messed up and I put the temperatures on the opposite side. I put 290 on top, I put 273 on the bottom. And my answer when I did that turned out to be like 14.2. I would have just moved on and left it like that if it wasn't for the fact that I looked at it and said, wait a minute, this is supposed to be a direct relationship. So one goes up, the other goes up, one goes down, the other goes down. My volume should be going down, not up. What did I do wrong? And so I rewrote it. And that's why I'm going to keep talking about this whole direct and inverse relationship thing because, if this was, say, a multiple choice test or something like that, you can be fairly sure 14.2 would have been one of the answer choices and you would have picked it and been incorrect. So be very careful. This is why I label V1, T2, T1. This is why I label all these things because I want to make sure that I'm putting the right thing in the right place. So rewriting the equation can be very helpful. Okay, so number 5, at what temperature with the volume of a gas, here's a volume. Um, if the gas had a volume of another volume, but this is in milliliters, that's not going to work, and another temperature. Okay, so at what temperature would the volume of the gas be equal to had a volume? So had a volume. So this is V1 and this is T1, which makes this T2 and this V2 very important. And I want to know T2. Okay, so let's rewrite this. Remember, volume and temperature. Here we go, Charles' law. Okay, so V1 over T1 equals V2 over T2. And I want T2. Oops. And so I am going to cross multiply to get myself there. So I'm going to do this one a little quicker. Basically, cross multiply means that V1 times T2 equals T1 times V2. Cross multiply. Okay. So therefore, T2 equals T1 times V2 divided by V1. So again, these ones and twos are super important. T1 is 144C, but what's wrong with that? That doesn't work for me. I can't use that. I need to add 273 to that 144 to come up with a T1 of 417 Kelvin. My V2, where's my V2? Here we go. Ah, that's in liters. That's cool. I can use that. So 0.796 divided by my V1. Where's my V1? Here it is. But that's in milliliters. That doesn't work. So milliliters, remember, it's 1,000. So let me just show you real quick the conversion. 1,180 milliliters. I want liters, so let's bring milliliters down and liters on top. 1 liter is equal to 1,000 milliliters. So 1,180 divided by 1,000 is 1.180. Now, in the future, you can do this a lot faster by just moving the decimal place 3, but that's why I'm doing it. Okay, so 1.18 liters. And if I type that into a calculator, my answer, I'm going to start doing ranges. So you're going to have to figure these answers for yourself too, is going to be somewhere between 280 to 282 Kelvin. Remember, to get credit for the review, you need to have the actual answer to 2 decimal places. But let's take a quick look and see, is this even possible? This is a direct relationship. So I do know my V1 and my V2. So I know my volume from 1.18 to 0.796. That means it went down. I know my temperature one was 417, so this makes sense. My temperature did go down, so this is within the realm of what I would be expecting. Okay. All right, 115 milliliters of a gas at 45.8 kPa and 57.2 Celsius. So I've got all kinds of stuff here. I've got a volume. I've got a pressure. I have a temperature. What is the volume? So I have another volume of the gas. I have a pressure, and I have yet another temperature. And so this here, one, two, two, two. Okay, so I'm going to use the entire combined gas law. The whole thing is mine. P1 V1 over T1 equals P2 V2 over T2. And I want to solve for, let's see, V2. Okay, so I want to solve for V2. So I'm going to cross multiply to get myself there. And that means I'm going to do P1 V1 times T2 divided by T1 times P2. So once you have this figured out, it's pretty much just plug and chug, and most importantly, converting units. So P1, where's my P1? There you are. There you are. Okay, don't really need to do anything with that. That's just in kPa, so that's cool. So 45.8 times my V1. Where are you at? You're here. 115 milliliters. Nope, that's not going to work. I need liters. So I'm going to divide that by 1,000 or just move the decimal place over 3. So 0.115 liters. T2, where are you at? T2, there you are, 112.3 Celsius. Once again, I can't use that. I need to hit that Kelvin. So I'm going to add 273 to that, and that is going to give me 385.3. All right, so I need this in Kelvin. So this had to be changed. This had to be changed. All right, now T1, where are you at, T1? Right here, 57.2 Celsius. And once again, that's not going to work out for me. I need to add 273, so 330.2 Kelvin. And then finally, my P2, there you are. And I can just use 99.3. So plug and chug in my calculator. I'm just going to put that all in at one time. It's going to be parentheses 45.8 times 0.115 times 385.3, close parentheses divided by parentheses 330.2 times 99.3. And when I do that, my answer is going to be in the range of 0.052, let's say 0.07 liters. Makes sense. My initial liters were 0.115, so not too far away from there. No giant changes, so there we go. And everything looks good. So make sure to put that in the calculator and put the actual correct answer for your credit. Number 7, gas has a volume. All right, another volume. At STP, ooh, that means I have both the temperature and the pressure. Don't forget that. It's going to get really confusing if you don't see that temperature and pressure and you start thinking, wait a minute, what am I doing? This is wrong. Uh, at what temperature? So I got another temperature. Okay. Would the volume of the gas be 78.31 liters? So I have a volume with a pressure of 612 mmHg. So this is a pressure. And so these are going to be my twos. Oops, I'm doing that. Two, 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 and one, one, one. Okay, so PV over T, basically same as the last one. P1 V1 over T1 equals P2 V2 over T2. And I am looking for V, oh, will be the volume of the gas. At what temperature? Okay, so what I want to solve for is T2. Okay, again, T2. That's what I want to solve for. I'm going to do that cross multiply magic. I'm going to do T1 times P2 times V2 divided by P1 V1 is going to equal T2. Okay, double checking my work here. Okay, so let's go ahead and put that into the calculator or put those into here. So what is my T1? My T1 is STP, standard temperature and pressure. And so that is going to be 273. What is my P2? Where are you at? 612 mmHg, that's fine. 612.0. And where's my V2? There you are, 78.31. It's already in liters. Sweet. Let's just go with that. So 78.31 divided by P1 V1. So where we go, P1 is part of my standard temperature and pressure. Now, standard temperature and pressure is 1 atm, but I don't want to do all that because I'm using mmHg. So if you recall, mmHg 1 atm is equal to 760 mmHg. So be very careful, make sure your units match. And then finally, I need V1, and that is 62.65 right here. There's my V1. So 62.65. And when I put that in the calculator, I'm going to double check my previous work. I'm going to put parentheses 273 times 612 times 78.31. Close those parentheses, divide that by 760 times 62.65. Close the parentheses, done. Let's see, same answer twice. I'm probably right. And so your answer is going to be in the range of 273 to 275 Kelvin. So go ahead and do that math and get me that correct answer to 2 decimal places and you're good. All right, what is the pressure of 1.27 liters? Oh, new page. Here we go. 1.27 liters of a gas. So here we go. Here's a volume. Here's a temperature. If the gas has a volume, here's another volume. And here's a pressure. Okay, and here is a temperature. And pressure is what it's asking. If the gas had, so here we go, this had a volume. That means this is my one, this is my one, this is my one. Very careful that you are reading the question so you know which one's your one and which one's your two. So this would make P2, P2, T2. And again, I would like to solve for P2. So P1 V1 over T1 equals P2 V2 over T2. And my wish, is to solve for P2. So let's do that cross multiply thing. P1 V1 times T2 divided by T1 times V2. So let's do a little plug and chug here. And P1, there you are, right there, 145 kPa. Okay, that means my answer is going to also be in kPa, which is cool with me because it didn't say any specific pressure, so fine. V1, here we go. This is why I keep labeling V1. I almost wrote this 1.27. Almost did that. But I wrote the ones and the twos, so I'm not going to make that mistake. So 875 milliliters, that's not going to work out for me. I need liters. So I'm going to move that decimal place, and I'm going to call this 0.875 liters because that's what I need it to be. And then T2, so remember I need 2, and that's 288 Celsius, and that's not going to work out for me. I need 288 plus 273, and that is going to be 561. Sounds like a good number. I'm going to divide that by T1. Where are you at, T1? There you are. 176. Oh, so close, but you just can't come to the party just like that. So I'm going to change that to 449 by adding 273. And then finally, B2, I'm almost done. 1.27. And I'm going to put that all into my calculator. And when I do, I'm going to get somewhere between 123 and 126 kPa. And won't you be excited when you figure out what the answer is and round it to 2 decimal places and put it in your answer sheet? Okay, 9. The atomic mass of chlorine is 35.453 grams per mole. The volume of 20 grams of chlorine of gas at STP is how many liters? Okay, so this one's taking a bit of a step back. This one is still gas, but it's kind of going more into stoichiometry. And this is something I've seen happen on questions, and it can be kind of confusing, which is why I put it in here. Now, this tells you the atomic mass of chlorine is 35.453 grams per mole. That's true for one chlorine, but chlorine gas, remember, chlorine is diatomic. So chlorine gas is Cl2, not just Cl. That is super important. You're going to see something just like this. So I'm going to start with my given measured quantity, which is 20 grams of Cl2. I'm going to move grams of Cl2 down. So remember, Cl2, well, let's put that to mole. And I want volume, so I have it in moles. So let's move mole down and go to volume, okay? Or better yet, liters. Uh, okay, so 35.453 times 2 is going to be 70.9 for 1 mole, and 1 mole of Cl2 or gas or anything is going to be 22.4 liters. So if I have 20 grams and each mole weighs 70 grams, I've got like about a third of a mole or so. But in my calculator, I'm going to do 20 divided by 70.9 times 22.4 to come up with my final answer. And that answer is going to be somewhere between 6 to 7 liters of Cl2 gas. Okay. So just because we're in the gas laws doesn't mean we can completely escape stoichiometry. It does pop up every once in a while. Just be very careful. Even though the question tells you this, you need to know whether or not it's talking about a diatomic and act accordingly. Okay, at what temperature would 0.46 moles of gas occupy 13.3 liters if the pressure? Okay, so I've got a temperature and moles. Let's come back to that. I've got a volume and I have a pressure, but what I don't see any changing here, right? So I am thinking PV equals nRT. I'm trying to describe the gas as it is, right? Now, moles, that's N. So I have P, V, N, and T. The only thing I'm missing is R. And let's see here, we're in mmHg. That's very important. So I want to find my R constant for mmHg. And here that is right here. And that's 62.4. So it's very important that I use that constant as my R. Okay, now what I want to solve for is temperature. And so let's just rewrite this. Okay, I want to solve for temperature. And so I'm going to divide both sides by NR, and R cancels on that side. And so T equals PV divided by NR. I just find it to be easier that way. UBU. Pressure is 734 times my volume, no one or two, because this isn't a change in state. So 13.3 liters. Okay, liters is what I want. That's good. N is the number of moles. Sometimes you get it in grams and you'll have to change it, but this isn't in grams, it's already in moles. So how cool is that? So 0.46 times R. And remember, once again, my R is 62.4 if I'm dealing with MMHG, which I am. So 62.4. Okay. And if I drop that bad boy into the calculator, my answer is going to be somewhere between 335 to 345 liters. So go ahead and do that math. And as long as your answer is within that range, then you are doing awesome. Okay, we are now more than halfway done. So let's go ahead and hit the home stretch here. Okay, how many moles? Oh, that's an N. Would occupy a volume. I got a pressure. I've got a temperature, and I don't have a change in state. So I'm thinking again, PV equals nRT, and I want N. Right, so I'm going to rewrite PV equals nRT to solve for N. And so N equals PV divided by RT. So let's go ahead and pop that in there. So P equals 132. Keep in mind, this is KPA. That's going to become important in a minute. Yeah. And V is in volume. It's already in liters, which is cool. So 157 divided by R. Okay, so for KPA, what's my R for KPA? Let's find it. There we go. KPA is 8.31. That's my R ideal gas constant is 8.31. So 8.31. And then finally, my temperature is at negative 16.8 degrees Celsius. And this is the whole reason we do Kelvin is we don't want negative numbers. That's pretty much why it's there. So 273 plus negative 16.8 is 256.2 Kelvin. Throw all that into the calculator, and you are going to end up with a final answer somewhere in between 9 to 10 moles. Okay, this one's pretty easy. Let's try to describe the relationship between pressure versus temperature and volume. This is kind of how I always remember this is PV equals nRT. If they're on the same side of the equal sign, for like pressure and volume, I guess you can see the picture and the camera, see the video here. So if I have a container and it's sealed and that no air is getting out and I reduce the volume, I crush this can, but all the air is still in there, then as the volume reduces, the pressure is going to go up. This is called the inverse relationship. One goes up, the other goes down, one goes down, the other goes up. Now, on the opposite sides of the equal signs, say volume and temperature, if I turn the heat on for, say, a hot air balloon and I increase temperature, the volume is going to go up. This is a direct relationship. One goes up, the other goes up. One goes down, the other goes down. So we covered that earlier, but this is personally how I remember it, is just looking at this formula. uh, is looking at that formula, and so that should work out for you too. So pressure and temperature, here they are on opposite sides, so these are direct. Pressure and volume, they're on the same side, these are inverse. One goes up, the other goes down. And volume and temperature, those right there, we just talked about those. Those are direct as well. So one goes up, the other goes up. One goes down, the other goes down. Okay, last page. 13, determine the temperature if a 25-gram sample of neon gas that exerts a pressure and has a volume. So again, I'm not talking about a change. I'm talking about that PV equals nRT. Okay, and then let's go ahead and this what we want temperature. And so I'm going to rewrite this by dividing both sides by nR to isolate T. So T equals PV divided by nR. Okay. All right, so let's see. This is in grams. So I can't just go and throw grams in for N. Well, let's see. I got a pressure. Let's put that in 0.922. Okay. And I've got a volume. Let's see where that. Here we go. 3.25. Already in liters, so convenient. And can't use it as is, but I can do 25 grams of neon. And grams of neon can be converted to moles of neon quite easily. Let's take a look at this periodic table and formula sheet. Okay, and where is it? There you got periodic table. There you go. Neon weighs 20.18 grams per mole. That's its molar mass. So cool. So 20.18, yes. 1.8, 1 mole. So I have 25 grams. I'm sorry, yeah, I have 25 grams. Each mole weighs 20 grams. So I'm pretty close to a mole. 1.24 moles. So let's put that in N, 1.24. That's kind of the hard part. And then R, well, let's see, I'm dealing with ATM, and on my chart, ATM, it's R 0.0821. So make sure you look those up. And then my answer in this case, I'm not going to give you a range because this is a multiple choice and none of them are anywhere near each other. And so the answer was 29.4, which is C. 14. All right. So here we go. This is more of a thought process one. Consider a canister of gas in a closed system where the temperature remains constant. This is important. Which of the following would increase the pressure in the container? So I want to make the pressure go up. So I'm going to kind of think about this thing. Okay, it's a closed system. So that means the amount of gas is going to stay the same and the temperature remains constant. So what can I do to increase the pressure? Well, increase the mass of the gas molecules? Nah, I can't do that. The gas molecules weigh what they weigh. CO2, I can't make CO2 heavier. So no. Increasing the rate of diffusion. I'm in a closed system, so that's not really a thing. So no. Increasing the volume of the container. Well, if I make the container bigger, that's going to make the pressure go down, and that's not what I want. I want to increase it. So that leaves me with decreasing the volume of the container. If it's a closed system, that's going to increase the pressure. Okay, Dalton's law of partial pressure. This one is pretty easy. basically what it's saying is the total pressure is the sum of all the partial pressures. So it kind of makes sense. So a gas mixture with oxygen, nitrogen, and carbon has a total pressure of 230 kPa. So 230 kPa is my total. Now the partial pressure of oxygen. So oxygen equals 100 kPa. And the partial pressure of CO2 is 40. So CO2 equals 40 kPa. Now, the only time these are going to be hard is say one of these was like mmHg or something like that. Then you would need to convert it because they all have to be the same. I can't say 12 inches plus 1 foot equals 13 something because that's not a thing. I have to make sure they're in the same units. Now, in this case, they already are, which is kind of easy. And then, so the nitrogen equals X. And so if I rewrite this, I can do 100 plus 40 plus X equals 230, or even easier, 140 plus X equals 230. And so X equals, I'm going to take the 140 and um, subtract that from both sides. So X equals 230 minus 140. And I will let you solve that one and pick A, B, C, or D. Okay, so starting with number 16, a cylinder with a movable piston contains a sample of gas having a volume of 6 liters in 1 atmosphere. The gas is heated. Looks like I'm dealing with a change, so I am going to start thinking PV over T. I'm going to think about the combined gas law. So what do I got here? I have a volume, I have a temperature, I have a pressure. The gas is heated, so this is 1, and these are going to be 2. So I have a temperature 2, while the pressure is held at 1 atmosphere. Okay, well, that means that, let's see, a P2. And what is the V2? What is the final volume of the gas? Now, I have some good news for you. In this case, because the pressure stayed at 1 atmosphere both times, that means that the temperature stay this, or sorry, the pressure stay the same. So basically, I can ignore it. I don't need to worry about it. So this is just a volume temperature question. Okay, and if you recall, volume and temperature, well, here's a good way to do it: is PV over T. So if I don't need to worry about pressure, I'm just left with V over T. So I'm going to think V1 T1 equals V2 T2. Okay. So again, I'm not going to worry about these pressures because they stay the same. Now, if you put this in the formula and did the math, it'd be fine. They would just cancel each other out. It's not going to be a problem. But I'm not going to do that. So V1, I'm sorry, I am solving for P, oh, I'm solving for V2. Okay, so if I want to solve for V2, I'm going to do my cross multiply, and that is going to leave me with V1 times T2 divided by T1 is going to equal V2. Yeah. All right, so let's plug and chug here. V1 is 6, so that's good. T2, not T1, but T2 is already in Kelvin. How convenient. So 303 divided by my T1, which is right here at 293. Okay, and so I am going to throw that into my calculator and end up with somewhere in between 6 to 7 liters. You'll have to figure that out. Just go ahead and round that to 2 decimal places and you're good. Okay. Okay, what is the total pressure of a container that has a mixture of hydrogen, helium, and argon? So we're back into adding together pressures. There's a name for it. I'll have to remember that. Dalton's law of partial pressures. Okay, so I've got helium at 42.7 kPa, argon at 54.7, and the partial pressure of hydrogen. So this is about as easy as it gets. It just wants to know the total. They're all already in the same type of pressure. So this is literally just 42.7 plus 54.7 plus 1.9. I'll bet you can figure that out. Add that all up together, and it's going to be somewhere between 97 to 100 kPa. So you will get some questions occasionally. They're just super easy. You can just fly right past them. All right, gas balloon with a volume of 106 liters when the temperature and the pressure is 740. What will its new pressure be when the volume and temperature change? Okay, so I've got all of them. I've got a volume, I've got a temperature, and I have a pressure. Whoops. I want the new pressure. This is what I want to solve for. And the volume and temperature. So this is a T2 and this is a V2. Okay. And I'm solving for P2. And so I like to write it out ahead of time. I've just been doing that the whole time, so I'm going to keep doing it. So P1 V1 over T1 equals P2 V2 over T2. And I would love to know what P2 is. So let's do a little cross multiplying here. So P1 V1 times T2 divided by T1 times V2. So let's go ahead and plug in those values. P1 is in mmHg. Cool. So my answer is going to be in mmHg, and notice so are my answer choices. So great. So 740 times V1, which is 106, times T2. I'm going to go down and look for my T2. Okay, and that's 293. And we're going to divide that by T1, which is already in Kelvin. So 318 times V2, which is 92.658. Okay, and then in my calculator, I'm just going to do parentheses 740 times 106 times 293, close my parentheses, divide that by parentheses 318 times 92.658. And if I do all of that, I am going to end up with an answer that is, well, no point in giving you a range because notice these are all pretty far apart from each other. So if you put that in a calculator, it's 780 mmHg. Two left. Okay, gas at standard temperature and pressure. Okay, so I already know temperature and pressure, standard temperature and pressure. What will the volume be if you have 2.4 moles of the substance? So in other words, I'm not looking for a change. I'm just looking to find out one of my attributes. So I'm thinking PV equals nRT. Okay. And so I've got P, I've got T, got N. Volume is what I want to know. All right, so let's go ahead and rewrite this. So basically divide both sides by P to isolate P. And so that's going to be N RT divided by P is going to equal my volume. N is already in moles. How nice is that? 2.4 times R. Now, which R do I use? Well, let's see. Standard temperature and pressure. Um, I am going to go ahead and go with a pressure of ATM because that's the easiest. And the R for ATM is 0.082. And my temperature, I've got standard temperature and pressure. So 273 Kelvin, which is the same as 0 degrees Celsius. And then finally, pressure. Now, here's the cool thing. Since I chose ATM, that's 1, so I can basically ignore it and just put 2.4 times 0.082 times 273 into my calculator. And that is going to give me, again, this is multiple choice, and none of them are even close to each other. So let's just go ahead and tell you. That's going to be 53.79. Last question. Gas gets heated from 30 to 50. What would happen to the pressure of the gas if the volume remains constant? Okay, so this is going to be volume and pressure, and I'm sorry, temperature and pressure. And so if I increase the temperature and the amount of gas remains the same, the more I increase the temperature, the more the pressure is going to increase. Oops. Looks like that. Oh, never mind. I did not. Yeah, 30 to 50. Okay, so temperature went up. Volume remains the same. So yes, pressure is going to increase as I bring that up. All right. Looks like we are done with this. So I will see you again for 10 and 11. That's actually going to be a pretty short one. A lot of information, but not quite as much repetition since we've done it recently. So.